Math 2414, Calculus 2. Calculus 1 review. Derivative rules, part 1. Before we jump into everything that is Calculus 2, it would probably be a good idea to review some Calculus 1 concepts because everything in Calculus 2 is built on what you already know from Calculus 1. But for full disclosure, it's also built on all the algebra you've ever seen and all the trigonometry you've ever seen, and I could say all, but we'll just say a lot of the geometry that you've seen. And when I say geometry, I mean what you saw in high school, but didn't necessarily take a college geometry class. It's just a continual building process. Everything that you've seen in the past is considered fair game, but I also know that not everybody remembers everything. So I will try to review and remind you of things from days gone by that you need to know as we go through Calculus 2. All right, so let's review some basic derivative rules. And for full disclosure, this is not the complete list. This is just the first of 4 parts for derivative rules. Derivative rule number 1. If f of x equals x to the nth power, then f prime of x is equal to, this is the rule most people remember. For example, if I asked you the derivative of x to the 5th power, you should know that it's 5x to the 4th power. But in general, the derivative of x to the n power is n times x to the n minus 1 power. You bring the power down in front as a coefficient, and then you lower the power by 1. Derivative rule number 2 is actually a specific version of number 1, but it's worth having its own rule. If f of x equals c, and it's worth noting that this c is a constant, so I'm going to write it out to the side. C is any real number, and it will make another appearance here. Then the derivative of any constant is 0. This kind of makes sense if you remember that the genesis of derivatives was measuring the slope of the tangent line of a graph. Well, if a function is equal to a constant, then its graph is a horizontal line. Because in terms of inputs and outputs, it doesn't matter what goes into the function, the same number always comes out. So as ordered pairs, all of your x's are different, but all of your y's are the same, so every point is up the same amount. Well, that's a horizontal line, and if the genesis of derivatives is measuring the slope of things, that slope is 0. So it kind of makes perfect sense that the derivative of a constant is 0 if you think in the context of slopes of tangent lines of graphs. Rule number 3, if f of x equals g of x plus or minus h of x, let me pause for a second. The goal behind mathematics is to make things make it impossible to misunderstand them. But in order to do that, we have to resort to symbolic representations when sometimes words are better. For example, this just says your function is the sum or difference of 2 other functions. That's all it says. So, if f of x equals g of x plus or minus h of x, then the derivative of f of x is just the derivative of g of x plus or minus the derivative of h of x, whichever one it is. In other words, it says to take the derivative of a sum or difference, you just take the derivatives of each individual term. I think most of you know that and do it automatically, whether or not you stop and think, this is the rule that I'm doing. Rule number 4. If f of x equals c times g of x, again, c is any real number, so we're saying that we have a number parked in front of another function. Then the derivative of f is c times the derivative of g. And again, I think that you know this already and you do it without even thinking. For example, if we had f of x equals 7x to the 3rd power and I asked you what the derivative was, most of you should be looking at this and going, oh, it's 21x squared. And by the way, if you don't know that the derivative of this is 21x squared almost instantly, then you need to seriously review your Calculus 1. That's a skill that I assume is automatic and doesn't need explaining. But just to point out what this rule is saying, this rule is saying if you have a constant in front of a function, when you take the derivative, leave the constant alone, take the derivative of the function after it. So over here, it's basically saying you would leave the 7 alone, take the derivative of x cubed, and according to rule number 1, it's 3x squared. And then after that, we've got some, I'll say algebraic cleanup, but it's really more arithmetic. 7 times 3 is 21. But that's all this rule is saying. If you've got a number parked in front as a multiple, let it sit, take the derivative of what follows it. Number 5, if f of x equals g of x times h of x, in other words, if your function is a product of two other functions. Do I got a red marker around here? I do not. I was about to write, wait, I do. I'll be right back. I'm just on the other side of the camera, don't worry. Getting my computer bag with all kinds of markers in it. See? All kinds of markers. But the reason I paused is because when you're doing math, calculus, or really anything in life, it's not only important to know what you can do, but what you shouldn't do, because it's wrong. When people first see the derivative of a product, what they want to do is say, just take the derivative of each half. Now don't write this down because it's wrong. I'm about to put a big old slash through it. The derivative of a product is not equal to the product of the derivatives. It's not like this rule up here that just says take the derivative of each piece. It's easy to do, but it's also wrong. You have to use the product rule. Now I remember why I don't like using red. There we go. You have to use the product rule. And there's a lot of gimmicky ways for remembering the product rule. But essentially for the product rule, you just take the product of one factor at a time. For example, let's take the derivative of the first factor, g of x, so g prime of x, times the second function, so only take the derivative of the first one, and then you add to that the product by taking the derivative of the other half of it, but leaving the first half alone. In other words, g of x times h prime of x. There's a variety of ways of saying this. Derivative of the first times the second, plus the first times the derivative of the second. But no matter what gimmicky way you remember the product rule, the essence of it is you just take the product of one factor at a time, and then you add the results together. And by the way, the product rule is extendable to more than two factors. Just to show you what I mean, and I'll throw it in a cloud right here. If you had f of x is equal to g of x times h of x, we'll say j of x. I don't like using I as a variable because it's the square root of -1. But if you had what I would call a triple product, the way you take the derivative of any product is one factor at a time. So for example, we could take the derivative of the first factor and leave the other factors alone. And then add to that the result of doing the derivative on the next function, so g of x times h prime of x times j of x. But then we would have to add a third factor to it. We'd have to add a third product to it because we have a third factor to take the derivative of g of x times h of x times j prime of x. So if you were taking the derivative of a triple product, you would just do one derivative at a time and leave the other two functions alone, and then just add up all the results. Same thing if you had 4 factors, 5 factors, or 5,000 factors. You would just take the product of one factor at a time, leave the rest alone, and then add up all the different ways of doing that. We probably won't be taking many derivatives of triple products, just standard products involving 2 factors, but there is a more generic product rule besides derivative of the first times the second plus the first times the derivative of the second. But know the product rule. And in fact, I would like it in green because I'm trying to put all the rules in green. Derivative of the first times the second plus the first times the derivative of the second. And by the way, since this rule involves multiplication and addition, and since both are commutative, you have some flexibility on the order. This product could be written first. This product could be written in reverse, as could that one. There's a lot of ways, a lot of flexibility because of the fact that it's addition and multiplication. All right, number 6. If f of x equals g of x over h of x, then f prime of x equals. This is the quotient rule. There's a lot of gimmicks for the quotient rule. but no matter how you slice it, it goes something like this. It's the derivative of the top times the bottom, so g prime of x times h of x, minus the top times the derivative of the bottom, so minus g of x times h prime of x, all over the square of the function on the bottom. Now, whatever gimmick you use to remember the quotient rule is up to you. I know a couple, I'm just going to share one of them with you. Most people remember that the denominator of the derivative is just the square of the denominator of the original function. Where people get mixed up is in the numerator, because unlike in the product rule, the numerator has subtraction, which is not commutative, meaning that the order matters. Meaning that you have to take the correct derivative on the left side of the subtraction and the correct derivative on the right side of the subtraction. One gimmick I heard is a little something that you say, low d high minus high d low over the square of what's below, d meaning derivative. That one's kind of corny. It works, but there was one student that showed me a gimmick that I use to this date, and I'm going to share it with you. I asked if anybody had a gimmick, and he said, Tibbet. I was like, Tibbet? What do you mean, Tibbet? Tibbet. T-I-B-B-I-T. And I had to ask him to elaborate. I figured the T meant top and the B meant bottom. But what's up with the I? And he said, well, the I is really the derivative mark. Derivative of the top times the bottom, derivative of the bottom times the top. We still have flexibility with the product over here. Multiplication is still commutative. But now when I do the quotient rule, in my mind I just think Tibbet. T-I-B-B-I-T. Meaning that the order that I do the function and the derivatives in is the derivative of the top times the bottom minus the derivative of the bottom times the top. Whatever gimmick you want to use is up to you, but you are expected to have the quotient rule memorized. And the product rule. Let's see how much time we have on this video. It feels like it's been going a while. At this point, I'm done reviewing these rules, but I am going to do one more thing that's kind of optional. But for those of you who are going more in the theoretical mathematics as opposed to applied mathematics, physics, engineering, and the such, I like to get a little bit more theoretical, because I personally am a theoretical mathematician. If you ask me to apply the math, I don't enjoy it anymore. So if you're good with your rules and you're not worried about the theoretical side of things, you can shut off the video now and you're going to be okay. But for those who are curious, and hopefully it's all of you, I want to quickly remind you where the quotient rule comes from, because when you're doing math and you forget something, that's understandable. There's a lot to just remember. But if you understand where it came from, you can sometimes reinvent a rule, such as the quotient rule. Actually, you know what? I'm going to hold off on doing that because it's going to use a rule we haven't used yet, which is the chain rule. So I recant. Well, I don't want to leave you completely hanging. If you want to prove the quotient rule, you can start by rewriting the quotient g of x over h of x as g of x times h of x to the -1 power, because -1 powers mean reciprocals. Then you can apply the product rule on this. You'll have to use the chain rule over here. You'll get an expression that eventually can be turned into this by getting a common denominator and adding fractions. So I'll leave it up to you to play with that if you would like.